graphical analysis. Graphical analysis of functions and modeling. Now the modeling we're going to do here is relatively simple. We're just going to sketch it out, mainly as a motivation as to why do we study this in the first place. So we'll introduce some things that we're not going to go into in detail, but it just kind of motivates for why do we even study this in the first place. Modeling is a very sophisticated thing, and that's our ultimate goal in any of the sciences. We want to construct a mathematical model that represents our data. Once we have that, we can work with that model and do projections and do different things. And that's exactly what's happening with the spread of the COVID. There is a mathematical, a computer model that they run on the computer, and they're estimating how many people will succumb to disease, what hospitalization rates. They set it all up, and that's their model, and that's what they do. They keep running their models at the various universities and making their projections. Now, the spread of the vaccine is not as precise as some of the engineering models that we do, because the laws of physics are much more precise. Here, it's more statistical modeling, what they deal with on the spread of COVID. But there is a mathematical model based upon probabilities of things happening. And that's why the numbers can be way off in the big ranges, because you can't know exactly what percentage of people are practicing best practices for it. So you do some estimates of it. Okay, so what are we dealing with? Well, so far in this course, we've introduced a lot of different functions. So we had a variety of different functions. We had polynomial functions. We had some of the radicals. We didn't do a lot with radicals, but a little bit with radicals, mainly finding their domains and a little bit of their ranges and stuff. We did rational functions. These were all considered the algebraic functions. Then we also introduced trig functions. As well as the inverse trig functions. And we looked at the exponentials functions and the logarithmic functions. The inverse of the exponentials called logarithmic functions. These were considered to be transcendental functions. And some of the properties that went along with them. So we looked at the various things. Some of the properties so far, we talked about things such as the domain of each of those functions. We also talked about the range. Domain is the allowable input values, and the range is what comes out. And we saw in certain cases the range could be restricted, and we were kind of played around with that a little bit. And we looked at, especially for the inverse functions, there's certain values you can and cannot put in and certain values you expect out. So we spent a lot of time on that. We looked a little bit about the graphs. We talked a little bit about the graphs of each of those. So you have a general sense for what a parabola looks like, what a sine and what a cosine look like, what an e to the x and what a natural log of x look like. So we have some general ideas about those functions, but not a whole host of information. We just introduce them in a little way. So we introduced these basic features related to the graphs, and then we went and then we did a lot of properties after that. And this is where the analysis came in. We looked at all analytical techniques. These are all the things that you're going to need when you get to the calculus. You get all these functions. You need to understand about the domain, the range, information today, more about the graphs, and some of the analytical techniques. Analytical trig, the analysis of finding the zeros of polynomials, all those were embedded in all these different things. And what we're going to do now is we're going to expand upon this. Because this is essentially where you start the calculus. Your objective in calculus is to analyze all these functions, going beyond what we did here. So if you have this as a starting point, the calculus will be so much easier. If you understand all of these functions and their domain ranges and their graphs and the analytical tools that we use to find certain properties and features of those functions, that is where you need to be at the end of this course. So this chapter here brings everything together. And this is probably one of the most important chapters to get you ready for the calculus. If you understand this, you'll have a leg up on that. So we're going to now take this and we're going to, in chapter 11, we're going to expand upon this. And look at each of the different types of functions, look at more of their properties that pertain to their graphs. We're going to detail it down to more properties. Not so much with analytical techniques, because we already have most of the techniques we have, but some of the properties and how to recognize them. Okay, so we start in 11.1 with the first thing, polynomial functions. So 11.1 is our polynomial functions. And what is a polynomial function? Well, we know what that is. We can write it either as an f of x, or how did I write it in here? P of x, I think it was. Yeah. We have p of x is equal to a sub n x to the n plus a sub n minus 1 x to the n minus 1. Keep counting down. A sub 2 x squared plus a sub 1 x plus a sub 0. That's an example of a polynomial functions. It's a sum of all, sum of difference, or a sum of all the power functions. So it's a sum of power functions. Meaning, here's a power function. F of x is a sub n x to the n. Those are our power functions. And we learned a few things about them. So far, what we know is, we know that the domain of any polynomial function is a set of all real numbers. So the nice thing about it here is that the domain of p of x is all real numbers. So the domain set all elements x such that x is a real number. That's all it is, very simple. Meaning I can plug anything in, it's not going to put a positive, negative, square roots, anything I want to put in there, and I will get a number out. It never, gives me an undefined quantity. Domain of all the allowable inputs. I can put anything into a polynomial function. And we also got some of the basics of power functions. We went over some of the looks of power functions. For example, let's take a look at n is equal to 1. So you might have your f of x, simply looks like, I'll take a sub n to be 1, x. And look at the graph of that. In this case, we have one possibility is this. This is my graph of that line of x. Now you could also have the coefficient being negative. So you could have another n is equal to 1, but where say I have minus 1 for that. Well, the only thing that happens here is my line goes from here down to here, slope of negative 1. Then I could go to n is equal to 2. This is again just for the power functions, and power functions make up polynomial functions. So if I take a positive coefficient, I have x squared, looks something like this. I could also have a negative coefficient, the negative of x squared. And what does it do? It just flips it down this way. Then I could do n is equal to 3, and patterns start to emerge. F of x is equal to x cubed something like this. And f of x is equal to the negative of x cubed. And it would look something like this. So we saw that early on in the textbook. So you should have a sense for that. Now if I go n is equal to 4, it would look very similar to this. But n is equal to 4 is going to look like this, but a little more flat at the bottom over here. N is equal to 5, very similar to this, but a little more, squeezes to the axis over here. Rises more rapidly here and shrinks more rapidly here. So it kind of does this over here, if n is equal to 5. But it keeps the same general state. And 6, more like this, 7, more like that. A plus and minus will do the same sort of thing. And you can see the domain is all real numbers. I don't have any problems with real numbers. So what is it that we want to address in this chapter? Well, we want to address not just the power functions, but what happens when we start adding all these power functions of lower degree than the largest degree in there. What happens to the shape of these things? So that's going to be the focus for 11.1, is the overall shape of a polynomial function. So we want to talk about the shape of a polynomial function. Beyond, this is my power functions, and now we want to expand it to polynomial functions, where I'm adding multiples of these and subtracting to each other. Well, there are two parts that come up that are very important. What we have is we introduce two different things over here. One thing we're going to introduce is something called a turning point. And we'll talk about what that is. This will dictate the potential shape of our polynomial function. And then the other thing we're going to deal with is something called the end behavior. We already know the end behavior of this, but we're going to find it's relatively simple when we get to a polynomial. So these are two aspects that we want to explore a little bit further. So let's start with a turning point, and let's define what we mean by a turning point of a function. The definition got messed up in the textbook over here. It kind of wrote over each other, so I'll write it out here. So we'll start with a turning point. So what is a turning point? A turning point on a graph, or a turning point on a graph of a function, and this applies not just to polynomials, but to any function, is a point where the graph of the function changes from increasing to decreasing. So is a point on the graph of the function where it changes from increasing to decreasing or decreasing to increasing. Go in opposite direction. Increasing to decreasing or decreasing to increasing. That's what a turning point. What do I mean by that? Let's get some pictures over here. So here's a function, and I'm going to do an elaborate looking function. This is actually a polynomial function. There's my function. Here's my x, and here's my y. So when it's increasing, I'm going to label that blue and put a positive. So over here, as I go in this direction, I always go from left to right, I'm increasing. I'm positive, I'm increasing. At that top of the hill, I'm no longer increasing or decreasing, but on the other side, I'm decreasing. I'm going down. As X increases, my output, my Y output goes down. So what does that mean? Well, that means this guy right here is a turning point. I go from increasing to decreasing. It occurs right there. Will always occur at that little peaks and valleys in my graph. Now this stays decreasing until it hits this point over here, and then I'm back to going up. So there's my low, and then my output Y goes up. So over here, there's another turning point. I went from decreasing to increasing. Now I'm increasing over here, and then on the other side I go down to decreasing. So over here I have another turning point. And last one over here, this is decreasing. On the other side of this, it's increasing. So here I have another turning point. That's what a turning point. Going from increasing to decreasing, or in this case, decreasing to increasing, will give you a turning point. And it always occurs at the peaks and valleys, if you will, the hills and valleys, if you will, of the graph of that function. And that has to deal with the shape of the polynomial function. So we know what a turning point is. Okay, is there anything that we can observe about turning points of these polynomial functions? Well, let me kind of go and introduce the second thing, and then we'll come back to the turning points and we'll see some examples. Because they're kind of related in some ways that we'll see. Restrictions on the turning point are defined by the end behavior. So that's what a turning point is. So at least you know on a graph you can pick it out. Let's take a look at the end behavior. And what do we mean by end behavior? And then we'll look at some examples out of the textbook. The end behavior of the graph of a function is what is the trend of the function as x, use the line, approaches infinity. That means x gets closer to infinity, gets very large, or x approaches negative infinity. So here's my x and y, and I want to see when I'm really out here, what happens to my function when x is really large. Does it do something like, this? Does it do something like that? Does it do something like that? What is the end behavior where x goes towards infinity, large values? Or at this end as well. Over here, does the function kind of, as I go this way, does it go upwards? Does it go, downwards? Let's just go to some fixed value over here. And this is as x goes to negative infinity. That's the ends, the two extreme ends of our function's graph. It's related to the graph of the function. So that's what we mean by end behavior. This becomes very important in analyzing a lot of different things because, if you know what the end behavior is, you know what the final, maybe an equilibrium state, or it may go into a turbulent state, and everything may just kind of go haywire, just blow up to plus infinity or blow up to negative infinity. But that can happen with the various graphs. Now, we saw this for the power functions. Let's take a look at our power functions. Again. So, since polynomials are just a sum of power functions, it makes that they are the dominant functions in a polynomial. Let's take a look at the power functions. And end behavior. So again, n is equal to 1, and I get f of x is simply equal to x. Here's my function. So what we would say over here is, as x goes to infinity, so as x gets larger and goes towards infinity, my f of x also goes to infinity. That's its end behavior. It goes to plus infinity because it's getting larger and larger. Or as x goes to negative infinity, and I'm going the opposite direction, my f of x also goes to negative infinity. Now, what if I take and flip this again, just like I did the other one? So I say f of x is equal to the negative of x. So the line, the graph flips down this way. And the opposite happens. So in this case, when I have a negative coefficient in front of that x, as x goes to infinity, my f of x goes to negative infinity. So I'm going positive infinity x. My y value, my f of x, goes down to negative infinity. And as x goes to negative infinity, my y value, my f of x, goes to positive infinity. It kind of flips over here. Negative to negative, negative to positive. That sort of thing. That's n is equal to 1. That's the end behavior of my linear function. That's what we're talking about. What happens at the end of the spectrum? Let's take a look at another one. N is equal to 2. So now let's take a look at f of x equal to x squared. What does the graph of that look like? Well, let's remember it's my parabola. So what happens here as x goes to positive infinity? What is my f of x? Well, that goes to positive infinity. So f of x goes to positive infinity. Now what happens as x goes to negative infinity? Well, f also goes to positive infinity. It goes upwards. On either side, it's going upwards. So f of x goes to positive infinity. Okay. Let's do the opposite of that. So f of x equal to minus the negative of x squared. What does the graph look like? Well, you should be getting comfortable that this is what the graph looks like. Something like that. Now over here, as x goes to plus infinity, my f of x goes to negative infinity. The y value gets getting more and more negative. And as x goes to negative infinity, I still go downhill. My f of x, or the y value, also goes towards negative infinity. That's a pattern. Notice what happened. This is n is odd. What happens? I'm going to two different extremes. N is even. They both do the same thing. Does that pattern follow? Let's try n is equal to 3. So continue over here now, n equal to 3, and let's see what happens. So n equal to 3. So I'm looking at f of x equal to x cubed. Now if we plug that in, we get something that looks like this. You can just plug it into your calculator, you get something that looks like that. Now as x goes to plus infinity, going to plus infinity, my f of x also goes to plus infinity. As x goes to the negative infinity, go in the opposite direction, my f of x goes to negative infinity. This is an odd exponent over here. It does the opposite things. Now, if I take the negative of that, it will do just the opposite, but it will still follow the same sort of trend. Looks something like this. And again, for this one, as x goes to plus infinity, now it's doing the opposite. It's that negative out there is driving it to negative infinity. So f of x goes to negative infinity. But notice, you're going to see these are going to do opposite things. As x goes to negative infinity, now I'm going in this direction, so I'm going up on that curve. My f of x goes to a positive infinity. Now this is always true. If n is even, notice plus infinity, minus infinity, minus infinity. If n is odd, plus and minus infinity, minus and plus. They do opposite things. So the n behavior is different for even and odd functions. So that's the important thing. The n behavior, if it's even, they're either both going to plus infinity or they're both going to negative infinity. If it's odd, one is going to positive infinity, one is going to negative infinity. Now, why is that important? Well, in any polynomial function, as I said, it's a sum of your power function. So, a polynomial function is a sum of power functions. So here's my polynomial, p of x. It's a sub n, x to the n, plus a sub n, x to the n minus 1, n minus 1, plus a sub 2, x squared, plus a sub 1, x, plus a sub 0. Power function, power function, power function, power function. Now, as n goes to either plus or minus infinity, the leading term will dominate. So the highest degree term will dominate. The leading term will dominate the shape of that polynomial function. Why is that? Well, for example, if I'm comparing, say, x to the 7th over x to the 6th, and if I take, x to be large, this is 10 times, this is a whole extra multiple. Say x is a million. This is a million to the 6th power. That's a million to the 7th power. This is a million times larger than that number. So that's the n and the n minus 1. At a million, this is 1 million times larger than the other. At a billion, this is a billion times larger than the other. So it really dominates it. So we can ignore all of the lower exponents. So we only focus on the leading term. Here's my leading term, and I can ignore all the other ones. So the n behavior of any polynomial follows the n behavior of the power function of the leading term, depending upon that sign. If it's positive or negative, it does different things. So that's what we want to address. So the n behavior of any polynomial function So the n behavior of any polynomial function follows the n behavior of the leading power function. So that's an important point. So we know that. At the ends, it's just these things we ignore. It becomes a power function. Okay. So that's an important aspect when we're examining polynomial functions. What happens in the end behavior? Now, how is this related to turning points? Well, let's take a look at that, and I'm going to explore that through the textbook here. Let me get it set up. Okay, let me share the textbook. This is right out of the textbook, so you'll have that as a guide. Okay, now let's explore some more stuff about turning points, if you will. So here, now I'm adding. I'm not just looking at power functions, I'm adding things. Now if you notice my f of x with either a plus 2x or a minus 2x, if I just change that, it changes from, in this case, going increasing to a decreasing function. Now if I look at my parabola, it looks like this. Notice here, for f of x equal to just, x to the first power, there are no turning points. This never changes from increasing to decreasing. So for a first degree polynomial function, there are 0 turning points. It's either always increasing or always decreasing. That's the truth. Now if I look at a quadratic, here's an x squared plus x plus 1, and then if I change the coefficient to minus x squared plus x plus 1, I look like this. This is a second degree polynomial. Both are second degree. How many turning points do they have? 1, because it's got one little valley here and one little peak over here. So they both have a turning point. One has the end behavior going to plus infinity, the other has the end behavior going to minus infinity based upon the leading coefficient there. These other parts of the power function, they just move it off the origin and they move it around a little bit. But now notice what happens when I deal with x cubed changing with an x squared and an x. Notice some interesting in-between behavior happens. Look at this. It goes up and goes down. How many turning points does this function have? Well, this function happens to have 2 turning points, one peak and one valley. If I put the negative in front of the x cubed, it flips, and now I still have 2 turning points, one valley now and one peak. It can also look like this. If I change the other coefficients, I could make it look like this. This has no turning points. Look what happens. This goes from, in this case, it's decreasing, 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 slowly decreases, and back to decreasing. So I either have 2 turning points for these two, or none for those two. An interesting feature we're going to see. We're going to develop not a proof of a theorem, but an observation that really can, if you want, prove as a theorem later on. But it's a very complicated theorem to prove. There's a lot of steps to it. Okay, that's a third degree. Let's take a look at a fourth degree, a quartic, if you will. It could look something like this, or it could look something like that. How many turning points does this have? Well, it only has 1 turning point. So fourth degree has a 1 turning point. But it could also look like this. I still have an x to the fourth, but now I have 1, 2, 3 turning points. If it's a positive, my end behavior goes to plus infinity. If it's a negative for my leading term, my end behavior goes to negative infinity. And how many turning points does this have? 1, 2, 3 turning points. Let's take a look at 1 degree higher and go to the quintic or the 5th degree polynomials. Here's an example of a 5th degree polynomial function. In this case, I have 2 turning points, 1, 2. This case, I have 0 turning points. And notice the end behavior, whether there's a positive in the front of that coefficient or a negative. It just flips the direction. Positive goes this way, negative goes that way. But is that the only set of possibilities for a 5th degree polynomial function? No, because they can look like this. I add more of the terms in between. Notice what I get over here. I now have 1, 2, 3, 4 turning points. This case gives me 2 turning points. What you will notice is that if you have an odd degree polynomial, you can only have an even number of turning points. If you had an odd number of turning points, then you'd be back to the end behavior doing the same thing. Meaning if this had 1 more turning point, there's 1, 2. If it went 3, it would then have to turn downwards, and that would not represent the end behavior of an odd degree polynomial. If I have an even degree polynomial, such as a 4th degree, how many turning points do I have? It's either 1 or 1, 2, 3. I can't have, 4. I can't have 2. If I had 2, then if, for example, if it was 2, if we go 1, 2, then I didn't have this turning point over here, number 11. It would continue to go down, so the end behavior would be that of a cubic and not a quartic. So this leads us to some observations that we want to talk about, the turning points and everything else related to these polynomials. So here is the observations we'll make, important observations. If the degree of the polynomial is odd, the left and right extremes of the graph goes in opposite y directions. Okay, that's the end behavior. If the degree is even, the graph goes in the same direction. So if it goes to plus infinity and it's even and you have a positive coefficient in front of that leading term, everything's going to go to plus infinity. If you have a negative coefficient in front of that leading term, everything goes to negative infinity if it's even. If it's odd, it does the opposite. And an nth degree polynomial function can only have up to a maximum of n minus 1 turning point. So if it's a first degree polynomial function, it has no turning points. If it has second degree polynomial, it's n minus 1 or 1 turning point. If it's third degree, it can have 2. If it's a fourth degree, it can have 3. A fifth degree can have 4. That's the only thing. It can have more turning points than the function degree itself. And furthermore, if n is even, the number of turning points must be odd. And if n is odd, the number of turning points must be even. So a fourth degree polynomial function can either have 3 turning points or 1 turning point. It can't have 0 and it cannot have 2. And if n is even and the leading coefficient is positive, then the graph of the polynomial function will always be increasing as we move away from the origin for sufficiently large x. So as x goes to plus or minus infinity, it's positive, everything's positive. If n is even and the leading coefficient is negative, then the graph of the polynomial function goes to minus infinity as x goes large. It's always decreasing. And if n is odd and the leading coefficient is positive, then the graph of the polynomial function will always come from minus infinity and go off to plus infinity. And similarly for the odd, it goes from plus infinity to minus infinity. So we kind of covered all these things about the end behavior of these polynomial functions. And there's some more information over here. And this talks about the end behavior, and this shows you more explicitly that as x gets very large, and I plot the scales here, and I put x plus 1, that 1 becomes indistinguishable from, this looks a lot just like f of x. And here's an x cubed. When x becomes very, very large, or an x to the 4th, no matter what I have over here, if these scales are very large, they follow their leading term. This is just illustrates that over here, the leading terms follow or kind of give you the end behavior of any polynomial function. Okay, so that's all we need for that. And here's some examples of determining over here, can you find the potential degree? So given the graphs of the polynomial function below, determine the sign of the leading coefficient, provide some possible choices for the degree of the leading term, and identify the end behavior of the function. Well, this has 1, 2 turning points, so it could be a third degree polynomial function. It could also be a 5th degree. It could be a 7th degree. We can't get the exact degree, but we know it has to be at least a 3rd degree. It can't be an even degree because it has an even number of turning points. And an even degree polynomial function has to have an odd, just the opposite. Now the leading coefficient, well, this looks exactly the opposite of, this looks more like minus x cubed or minus x to the 5th. So the leading coefficient for this must be negative. Okay, take a look at this one. Let's see, how many turning points? 1, 2, 3, 4. So this could be a 5th degree polynomial function. It could also be a higher odd degree, 7th, 9th, etc. Now this, if I look at a 5th degree, and it would kind of go this way, and then, it would go back up. So this would have a positive coefficient. You can just compare it to x cubed if you want to. Just compare it. It doesn't have to be compared to an x to the 5th, but an x cubed or an x squared for the even degrees, and that's all you need. So it has a positive coefficient. This one over here has 1, 2, 3, 4, 5 turning points. So it could be a 6-degree polynomial, could be an 8th, could be a 10th, an even degree or higher. Why is it even? Because these endpoints go in the same direction. Since these are going down instead of up, I know the leading coefficient has to be negative. So this is more information about the graphs, if you will, of these polynomial functions. So that's what I want you to take a look at for now. What we're going to be doing, and also establishing the end behavior and turning points, etc. What we'll look at tomorrow is, a little bit more in the domain and range. Now that we have that, we know the domain, it's the range we're going to focus on, as well as a little bit on the things called the modeling of polynomial functions. So for today, I just want you to take a look at some of these problems, since we're pretty much out of time right now. Let me put the homework up here, what I want you to look at, and we'll kind of finish up the other stuff as needed. So here's our homework. Essentially, they're graphs that we're focusing on right now. So right now, what we've looked at the end behavior. And we found that if it's an odd degree polynomial, it'll either look like this at the ends or flipped at the ends. That's an odd degree at the end of the, x being large and a positive, towards positive infinity and towards negative infinity, towards positive and negative infinity. This depends upon the sign of the leading coefficient. This is that the leading coefficient is positive, and this is the leading coefficient is negative. We also have a even degree polynomial, and its end behavior will look either like this, or it will look like this. And this is the leading coefficient is positive, the leading coefficient is negative. So that's the end behavior. We also looked at what happens in between the ends over here, and that deals a lot with turning points. Those are max and mins, little peaks and valleys, if you will, of the graph of our function. And it is related to the degree as well. If you have an nth degree polynomial, and n is even, then you can only have an odd number of turning points less than n. It could be, if n was to the sixth power, you could have a fifth, you could have a third, you could have a first, but you can't have a fourth, second, and 0. So if n is even, you have an odd number of turning points. Now, why is that? Well, if you had an even, then your odd degree n behavior, which looks like this, would have to go like that. And even turns will bring you both going back to the same number, same direction in the end. If you have an even number of turns, if you will. An odd number of turns will kind of give you the other thing. So if n is even, you want that behavior. And if you had an odd number, an even number of turning points, you can be back to the same sort of issue right here. Now, if n is odd, you have an even number of turning points, where they're less than n minus 1, n minus 3, etc. And it's the same thing over here. It's like n minus 1, n minus 3, etc. until as many you go down to 1 or 0. And this again is n minus 1, n minus 3, etc. So that's information about what the graph of a polynomial function looks like. Now you can't tell going in if it's an even 6-degree polynomial. You can't tell just by looking at it if it's going to be 5, 3, or 1. If it's odd and it's a 7th degree, you can't tell whether it's going to be 6, 4, 2, or none, 0. 0 is considered an even number of turning points. Okay. So that's what we did yesterday, and we kind of focused on that. We're going to look at now some more aspects of these polynomial functions as we analyze them in their graphs. So today we'll introduce two other applications and then, or two other properties, if you will, and then we will look at an application of polynomial functions and talk a little bit about modeling using them. This is not a course on modeling, so you're not going to have to go through modeling, but I wanted to mention something just in passing right now. Later on, if you do go on in mathematics or any of the sciences, engineering or whatever science, you use mathematics to model phenomena in the world, and that's why it's critical. Polynomials are used a lot, especially in software that's out there that's used for modeling. So we want to look at two other features. One is revisiting something we've already done before, and the third aspect is going to look at another look at the domain and range, just to refresh our memory. Now, we all know that the domain of any polynomial function is all real numbers. So that's good for, any polynomial function. The domain is a set of all x that says x is any real number. So that doesn't change. The range now, with the advent and looking at turning points, that becomes critical. The domain is all about the x's, and the range, that is a little more problematic. That requires some more analysis. And right now, the only thing we can do is approximate the range for most of them, unless it's an odd degree polynomial. So the range is broken into two parts. We have an odd degree polynomial, and in that case, the range is easy. The range in that case is set of all elements y such that y is any number, any real number. Because the end behavior takes care of that, because that's what happens. The end behavior goes to plus and minus infinity, and in between it might wobble and wiggle, but it's still not going to change that. Where the problem occurs is if you have an even degree polynomial. Because we know the end behavior can look either like this, or it can look like that. Now, what happens in between, however, is critical. What is the lowest point it takes over here? What is the highest point it takes over here? So to analyze these, what we're going to do is we're going to do this and estimate the range. So for these sorts of problems, we're going to estimate the range graphically. Either use your TI calculator or use a software program on the web. So we're going to estimate the range graphically. So let me kind of show you what we mean by that then. So this is all repeat. We've done the domain and range, but I think it's good to see it several times. So by the time you get to the calculus, it'll all make sense to you. It'll be simple enough and easy enough. So let's take a look at a problem. I'm going to go to Desmos, and let me just put the problem up on the board. So we're going to look at an even degree polynomial, f of x is equal to minus 2x to the fourth, okay, minus 3x squared minus x minus 1, minus 3x squared minus x minus 1. Now, I know this is an even degree, and I have a negative coefficient, so I anticipate my end behavior to be looking like that. That's the end behavior of that polynomial. What I want to find out is what happens over here. What is the maximum value? Because there's going to be some maximum value for the range, and then after that, it's all less than that. So we know the domain. The domain is all real numbers. Now let's see if we can plug that in and try and estimate what the range is, the output, the y values, if you will, of that function. So we'll come over here and we'll enter that in. We'll put, y equal to minus 2x to the fourth. And then we have minus 3x squared and minus x minus 1. And here it is. We can see the graph of our function, and it's doing exactly what I said regarding the end behavior. It goes down. The range is everything beneath this little top point called the vertex. So if I click on that little point over here, it's the y value. So we can estimate the range over here as being y being less than or equal to approximately equal to negative 0.918. That's all it is. Very simple. You could also do that on your TI calculator. It's a little more involved. This is, I find, so much easier. And I think there's a way of allowing you to use this on the test. So I'm going to be looking at the next test in the final exam and see if that's an option, because I think this is a great little tool to use. So from that graph, we can estimate the range. So if the range is the set of all elements y, such that y is a real number, and y is approximately less than or equal to minus 0.918. I looked at it correctly. So there's a range. We have all of that there. Okay, simple enough. That's all you need to do. Now, if it's a different one, look at your graph, pick the peak value for the even one. Now, sometimes it can look like this. You could have something that looks like this. And then I'd look for the, not this peak, not that valley, excuse me, but this valley. And I'd look for everything greater than that. This is less than that because of the end behavior, and you can see the graph. So you should have a sense for the range, the output values of a polynomial function. This should be relatively simple and easy. And you can see it, visually in the form of a graph. Okay, let's look at the next feature. This is the last feature, and then we're going to look at an application of a very simple quadratic polynomial function that is used in your elementary physics classes and beyond. Okay, the next thing has some connections to algebra as well. So the fourth property that we're looking at is something called the, kind of the oddness or evenness of the function. Okay, let's take a definition algebraically, and then we'll talk about what it means graphically. So here's the algebraic definition. So a function is said to be odd if f of x is equal to the negative of f of x, meaning the sign can come out of the argument. So there's one definition over here. In a similar vein, a function is said to be even if f of the negative of x is just f of positive x. The sign doesn't matter. Now, if you're looking at what this means graphically, this is what it looks like graphically. Here's a function, an example of a function that is odd. We say that this is symmetric about the origin. I'm going to describe how do we know that's odd. We say that it's symmetric about the origin. So what does that mean? Well, that means you do two rotations and you get the same thing back. So it doesn't matter what order I do. One thing I could do is I could rotate about the y-axis to test for this symmetry. You want to test for this symmetry. Here's the test. rotate about y-axis, then about the x-axis. So then rotate with the y, so it would look like this now. And then I'd rotate this about the x-axis. And what would I get? I get the same function back. If you do that and you get the same function back, we say that it's symmetric about the origin, and that is said to be an odd function. This is how we can see it graphically. Just kind of rotate it about one and about the other. Then we have an even function. An even function, look at it graphically. Here's a common example of an even function. And it might look something like this. This one is symmetric about the y-axis. Symmetric about the y-axis. And the test is you just rotate it about the y-axis and you get the same thing back. If you get the same picture back, it's symmetric about the y-axis, so it's considered to be an even function. And you're going to notice that this always is associated with an even degree polynomial, not just the leading term. So you got to be careful. It's not just the leading term. This is what kind of shows you where it might fail. In this case, to be symmetric about the origin, all the terms in that polynomial must be odd. It must be odd. Over here, all the terms in the polynomial, we'll see, must be even. Okay, so let's take a look at that. Now we're going to look at it algebraically. So there's our picture. Let's see how to go test algebraically. That's the beauty of the mathematics that René Descartes gave us, is we have a pictorial view of it, a geometric view, as well as an algebraic view, and there's a connection. Then you can actually look at the algebra and see a picture. And that's what makes it so useful to make that connection, all through René Descartes' Cartesian coordinate system, connecting the algebra to geometry. So let's take a look at, we're going to take a look at some functions, and we're going to be testing for oddness and evenness. So what we want to do is determine if the following functions are odd, even, or neither. Function doesn't have to be odd or even. It could just be none of the above. So let me have you try some of these. I put the algebraic definition. I will go through it, but see if you can figure that out on your own. So I'm going to put one over here and see how it works. So test that one. That one and this one over here. And that one. Test those straight and see if you can see, are they odd, even, neither? What do I have over here? And I'll put the answer up and we'll prove and or validate that. Let me do one more too, just so you can see that. So try that f of minus x and see what you get. If f of negative x gives you the negative of f of x, it's odd. If it gives you a positive f of x, it's even. If it doesn't satisfy that condition, it's neither. And showing it is the important thing. Okay, does anyone want to see how I was able to show that 1 is odd? Do you want to see how I proved that? Just raise your hand if you think you want to see that. Okay, so let's kind of go through that process here. Let me get rid of this up here for now. I'm going to work it over here. So the test is the same for both of them. I'm always going to be looking at f of the negative of x. So let me do that over here. F of the negative of x is equal to minus 3. And everywhere I have an x, I'm going to put in a negative x. Okay. Get rid of this. I don't need this anymore. So everywhere I have an x, I'm putting in a negative x. Okay, now let's carry out the algebra. Well, that's a negative 3. If I raise that to the 5th power, I get times a negative x to the 5th. And now the parenthesis gets removed. That's negative x times negative x times negative x assigned as negative. This gives me a minus 2 times a negative x cubed. Negative x times negative x times negative x is a negative x cubed. Not negative x quantity cubed, but negative 1 times x cubed. And over here, I can simply write that over here as, my minus plus a negative x. Okay, let's carry out all these signs. This is a negative times a negative, so that gives me a positive 3x to the 5th. Negative times a negative gives me positive 2x cubed minus x. Okay. Now let me factor a negative outside of everything. So I want to factor out a negative 1. I'm going to pull a negative out front. And what do I have over here? Well, this gives me a negative 3x to the 5th, a negative 2x cubed, and a positive x. I factored out a negative. But now I notice something, that this is identical to that. So this is actually equal to the negative of f of x. That is my definition of oddness. I was able to show that when I put in a negative x, factor out a negative, I end up with my original function with a negative out front. That's what we mean. That's the algebraic definition of oddness. That means it's symmetric about the origin. Okay, does anyone want to see number 2? Why that is an example of a neither case. Neither odd nor even. Anyone want to see that? Anyone get that? Let's kind of go through. So same process. Don't change the process. F of negative x. So everywhere I have an x, I'm going to replace it with a negative x and see what happens. Okay, let's do the algebra. So this is a 6 negative x squared gives me a positive x squared. And 4, negative 4 times the negative x gives me a positive x plus 1. Now, if I try to factor out a negative, let's see what happens there. I could try that. I'm testing for oddness. Pull out a negative, I get a negative 6x squared minus x minus 1. Now, that does not look anything like the original, because that's a negative, that's a positive, that's a negative. Well, it should be a 4, excuse me. There's a 4. And that's the same, but the last two are not. So I can say it's not odd. Is it even? Well, it's almost even. So odd it's not. But now, okay, I have a 6x squared and a 6x squared, and I have a 1 and a 1. But here's the problem. This is a negative 4, that's a positive 4, so it does not equal f of x, and it does not equal the negative of f of x. So it's not even, it's not odd, so it's neither. I can't fit it in that form. So it doesn't satisfy either of those conditions. And here's the trick, the easy way out. Odd, odd exponent, odd exponent, odd exponent. If it was even, this would be even if that negative 4x wasn't there. Right? That 6x squared plus 1, that would have turned out to be even. Because there's 2, this is 0, and we're considering 0 to be an even exponent. Does anyone see that? And I want you to verify this. Don't just tell me on the test, odd, even. I want to see the work. I want to see you carry out these algebraic manipulations. There's a purpose behind that. You need to do a lot of manipulations algebraically in the calculus. And if you don't practice it at this level, if you just remember little facts, you're not going to go very far. You're going to get stuck very early on in the calculus. That being said, anyone want to see how 3 is even? I want to see how I show that it's even algebraically. Okay, so let's kind of do it. I can get rid of this for now. I already showed that. Let's do it right above it. And again, what we do is we replace all the x's with the negative of x in that polynomial. So here's my polynomial. F of my input is 5 times my input to the 4th power minus 3 times my input squared, subtracting 2. And what am I putting for my input? The negative of x. And then I do the algebra. Well, it's 5, negative x times negative x times negative x times negative x is a positive x to the 4th. Minus 3, negative x times negative x is x squared minus 2. But now I look at this, it's identical to that. They're the same. So f of negative x is equal to positive f of x. This is my definition of being even. Very simple. And this other one you're going to see is neither. I'll just do it anyway. I have f of my input is minus 2 times my input to the 7th plus 3 times my input cubed minus 2. Well, my input is negative of x. So this gives me a negative x to the 7th, which is negative times negative, gives me a positive 2 times x to the 7th. This gives me a negative x cubed, so it gives me a minus 3x cubed. This doesn't change, so that's it. Now, if I can see that it is not the original one, because the original one, looks like this, so it's definitely not the original one. Is it odd? So I test that. Pull out a negative in front of that. Yeah, negative 2x to the 7th plus 3x cubed. Well, here's the problem. Then I get a plus 2. This is the same as this, but that is not. Because of that constant, because that's like an x to the 0th power, and 0 we consider to be an even number, it is neither. In that case, it's an example of neither. So that's how you do it. You just test it for oddness and evenness. This is going to become an important thing. You will see later on in some symmetry aspects of things, you will do this. Okay. So that's it. those are the new properties we wanted to introduce about polynomials. We wanted to talk about their end behavior, the turning points and how the number of turning points is related to the degree, how the end behavior is related to the leading term and leading coefficient of that polynomial. We talked a little bit about now more information about finding the range, and we're going to do it graphically. In the calculus, we're going to develop a tool that will enable you to do it more precisely. So you'll find exact values. Today we're just letting the calculator or the computer application give us an approximate value for the range. And then oddness and evenness of a function. So it's odd if I replace x with negative x in the function and I get the negative of the original function. It's even if I replace x with negative x in the argument of the function and I get the same function back. That deals with a symmetry argument. And it kind of makes sense. Maybe I'll do this to make that final connection with the geometric aspect of it. We did the algebraic and the geometric. Let's show what it means and what's happening over here. Let me just visually close this out with a visual link between what we're saying about oddness and evenness and the algebraic form. So again, this is our test. F of minus x, negative f of x, that means it's odd. F of negative x is equal to positive f of x, that means it's even. Well, graphically, what's happening here? So say this is my original function. I have an odd function. So there's my f of x. If I replace x with negative x, what happens is all the x's that were positive come negative. So I switch it around over here, and it goes this way. This is f of negative x. Notice that's not the same function. However, if I take the negative of this, meaning I now flip it about the x-axis, I get a graph that looks like this. So here's the negative of this. So here's the green, and it does this. And this is the negative of f of negative x. And that gets me back to that expression over here, because it just flips that over. Now, if I do the even, that's a little easier to deal with. So here is my even function. Here's my f of x. And then if I replace x with negative x, the only thing that happens here is that it just flips it around this way again. And that's f of negative x. So you can see it's even. Gives me the same function back graphically. So that's the kind of the geometric description of why that algebraic test is a test that kind of works. Okay. Well, that being said, let's close that out. Now let's take a look at this idea of modeling. We use a lot of functions to model things in the real world. We want to find out how things are related to each other. It's always looking for a cause and how one changing variable may cause another variable to change. And that's what it is. We look for mathematical models that we can use to predict what might happen. Just like they have right now a COVID model that they're working on at the various universities to kind of predict what's going to happen in the future. It's all mathematical. That's more of a statistical model. We're looking more of a direct algebraic model. And let's take a look at polynomials. They are very, very useful at modeling things. I'm going to kind of read through the textbook. I'm not going to hold you responsible for this part of it, but for the last application I will. But I do want to at least kind of make you aware of some of these things, because you will be going into various sciences and you're going to be using mathematics all the time to come up with models to make predictions about things. So let's take a look over here. We already did all of this today, and we have that stuff. And odd and even polynomials. Okay, here's where we're talking about modeling. Now, as I said, math is used to model phenomena, but by constructing a mathematical representation of known data points that describe the phenomenon. For example, you might have these data points, and if you were to plot them on a graph, you get these data points like that, and you could see that you could fit them reasonably well to a parabola. And here's the parabola, 0.1 x squared plus 0.4 x plus 3. Now, the beauty of this is if you ever use Excel, Excel has a little regression tab where you can kind of pick a quadratic, a cubic, a line to try and model data, and it will tell you. So if you take a course in statistics, that will tell you how to get this precise model. We're not focused on that. But that might be a representation of your model. Now, the benefit of that is not only do you have the model at discrete values in between, at discrete values, but you also have it at all the values in between, because I can get an estimate for my model. Instead of at 5 and 10, I could do it at 7, 8, 9, or 7.389. I could get all the stuff in between. So this now gives me a model over a full range of values. And that's what we use. That's what we mean by modeling a phenomenon. If I take measurements and they have a certain shape to them, I try and fit that to a polynomial that will replicate my data. And then I assume that it kind of follows that path in between the data values. So this model is good for all the in-between values, not exactly at the point. Now notice these dots do not fall exactly on my parabola there. And that's understandable, because when you make measurements, there's always error in your measurements. It's not precise. There's error in everything you make, and that talks about the error. But that shows you that you have a reasonable model for your data. Okay, now what you're trying to find is what we call the best fit model, and it accurately represents our data. But also, you use the model for values, as I said, between the data points. That is called interpolation. We say that this model interpolates between, say, this data point, 1531 over here, and this data point, 1018. It also interpolates to this data point, 5, 7, or interpolates between that data point and 0, 3. Interpolates, in between, if you will. Now, sometimes you would like to extend your model beyond the data sets. My data point ends here. I would like to see, does it go in the same direction? Which direction does it go in over here? That is called extrapolation. When you go either to the left of your last left point data point or to the right of your last right point data point, that is called extrapolation. You go beyond your interpolation. So that's extrapolation. This is where polynomials can be a little problematic over here. Because, they're easy to construct, but what if your data point, if you took a negative value for x over here and it went down over here? Well, what happens for the parabola? The parabola goes up. So this is only good in a certain range. Sometimes the models don't fit everywhere, so you have to be careful with that. And you don't get exact values. You get approximate values on the graph, on the curve for what they are, but not the true exact value. Okay, why are they important? We see that they can be useful to model data that takes on a certain shape. The reason polynomial functions are used more than any other function in computer models is that they're simple to construct and easy to use. And the properties of polynomial functions are well understood. We kind of do it in Algebra 1, and we do it in pre-calculus, we do it in calculus. We study polynomial functions all over the place. So we understand their properties and understand how they work. And they are very useful for modeling many different types of phenomena simply by choosing the coefficient of a sufficient number of power terms appropriately. However, they do have limitations. One of the problems is with interpolation. We know if I take a higher degree polynomial function, maybe the graph I want, this is my original data points, okay? That was the same exact data points I had over here, but this I was modeling this with a second degree. This is modeled with a much higher degree polynomial, and what happens? You get all those turning points in between, and that messes you up. So you have to be very careful. You can overdo it with a polynomial function. So this could be, I have 1, 2, 3 turning points, so it could be a fourth degree, and it probably is a fourth degree polynomial function, and it would not represent my phenomena very well. So that's a cautionary thing. You have to be careful about interpolation. Extrapolation can be a problem as well too, as I said. You know, say for example, this is what you have, but your real data, instead of turning around over here at this right turning point, it's supposed to continue going upward. That could be a problem. Interpolation and extrapolation are a problem. They don't model what we call asymptotic behavior or what we call singular behavior. Asymptotic behavior says, like, if you look at the end behavior, instead of going to a, infinity plus or minus infinity, you may go to a constant value. Well, polynomials can't do that. They either have to go to plus or minus infinity in one way, form, shape, form, or another. So there's a problem there. And this last one I won't talk about too much. It's a shape degree trade-off. You know, how you pick that, the perfect degree can be problematic. So polynomial functions can be very useful. If you go through all these engineering software, there's a lot of them that are called finite elements, finite differences for solving different phenomena. The fluid flow software, for the most part, they interpolate with low degree polynomials. Sometimes they're squares, a lot of times they're linear, and they do a lot of things called interpolation. But they are the backbone of most of the software that's out there in the engineering world. But there are problems, and there are ways around it, but you have to understand that. Okay, so let's instead now, we talked generically about modeling. Let's just end with a very simple sort of problem called projectile motion. This is one that's modeled perfectly by a parabola, because that's how, when you take an object and you say you shoot it up, it'll go up, and due to the force of gravity, we know it comes down. The interesting thing is that the shape of that height curve over here, h of t is the height curve, will always be parabolic. Why? Because the acceleration, initial acceleration that you're giving it goes like this. The initial velocity and the initial height all fall into a very simplistic quadratic or parabolic model, where a, get 1/2 times the acceleration times the time squared, plus your initial velocity v0 times the time, plus the initial height you're at is h0. Now a takes on different values if you're dealing with the metric. It's 9.8 meters per second squared. That's the kind of the pull of gravity. It's negative because it goes against the height. The height is measured from the surface of the Earth up, where gravity pulls down towards the surface. So it's always a negative acceleration. You're accelerating towards Earth. And the English system is 32 feet per square second. So let's take a look at a particular model. We say an object is launched from a height of 100 meters and at a velocity of 20 meters per second. Now find the model for the motion of the projectile and find the time it takes before the projectile hits the ground. Okay, so we start with, this is the basic model. My height is the acceleration plus the velocity and over time plus the initial height. So I plug it in. Now, since it is a metric model, I use the 9.8, divide that by 2, and I get minus 4.9. That's minus 1/2. 9.8 is minus 4.9. T squared plus 20t plus 100. Now we need to find the time when the height is 0, when it hits the ground. We're assuming that this was launched at a height that was, 100 meters up. And then we want to find out when does it come all the way back down to the surface of 100 meters beneath that. So that is when h is equal to 0. So we want to solve a simple polynomial equation, a quadratic equation. Plug it in for 0. I put 100 in for 100 meters for the h. 20 is my 20 meters per second. Plug this in, go to your quadratic formula, and you get two solutions out. So one solution, you get a negative time. Well, negative times we throw out, because that's assuming that if this was a true parabola, it would have come back in a negative, roughly 3 seconds, and it would have been on Earth again. But here, we're launching it from here, so only time being positive makes sense. So after 7 seconds, it will shoot up, and then after 7 seconds, the height will be 0. Now, this is not the path. I should point out that this is not the path that the object will take. The object is simply going straight up and down. This is how it looks over time. Now, time is over here, not distance over here. So this is not being launched over here. That's a different sort of problem. The h is just going up and down, and this is how to find the h value. And time is a secondary point over here. And that's all it is, a very simple little model for that. And I'll have you work a couple of different problems on that in the textbook. Okay.